So the magnetic force is given by this equation Q VB sine theta. When a charged particle having a charge Q moving in the speed V in a magnetic field B, making an angle of theta with the direction of the magnetic field, the direction between the velocity and the magnetic field is theta, like that picture shown here. Then this is the magnitude. You can get the direction by writing this as a vector equation here. So the direction of V cross B, the two vectors V and B, you get it from the right hand rule. Then you curl your fingers from V to B through the small angle. After placing them tail to tail, the thumb will be the direction of V cross B. And then you have a small problem with the Q. If Q is positive, it is from the right hand rule. If Q is negative, you have to switch the direction. So here this picture again, how to get the direction by using your right hand. So this is called the right hand rule. And you curl your fingers from V to B. The curling should be done in the plane formed by V and B. Then thumb will show the direction of, if it is a positive charge, that will be the direction of the magnetic force. If it is a negative charge, you have to flip the direction. So we did this quiz. Okay. So here we again looking at the same thing with both positive and negative charge. So I hope you can visualize this three-dimensionally. So this is the cardboard where we have the velocity in that plane, and the magnetic field is the green arrow, say out of the board. That not the screen, the yellow board that is shown. So V cross B, using the right hand rule, fingers in the direction of V. V is up, right? And then the direction of V, and you curl it towards magnetic field, and the thumb is pointing as shown here. Since it's a positive charge, no flipping. But for a negative charge, when you do the right hand rule, you'll get the direction of V cross B like that into the board. I mean, if it is into the board, but you have to switch the direction because a negative charge, then it comes to out of the board. Right. So you are looking at both positive and negative charge and how we are getting the magnetic force direction. The flipping happens only for the negative charge.
Like how this would be
okay. Yeah, all right. So this is, I mean, imagine we are the yellow cardboard is like this. Okay, this is the plane, and the magnetic field is like this. Magnetic field is this my remote control. Okay, there is the green arrow, and the velocity is my pen. Okay, so you got it, right? So you have velocity. Sorry, this is velocity. This is the magnetic field. So V cross B will into the board. So that F is into the board. In velocity is this red here. Okay, into the board. So that's what you are seeing, into the board. Okay, right? It's positive charge, you don't switch anything. But if it's a negative charge, into the board become out of the board. All right? Okay, so let's go to the next slide. We can now do a question. A proton, immediately you should say it's a positive charge, right? Proton is positive. So we have a positive charge, has a certain speed, let me call it the V, the magnitude of the velocity, the speed is that. through Earth's magnetic field. So, there is an Earth magnetic field. The value of the magnetic field is 55 microtesla, that's given. When the proton moves eastward, so here we have this direction. So the board is vertical here, and east direction is, let me take to the right. So this is the east, and the west will be the opposite direction. And up on the board, okay, and down also on the board down. So the east, west, and up and down is the plane of the screen. What about the north? North will be into the board. Okay, so if we use our convention here, it's not really cannot show into the board, right? It's a two-dimensional thing. So actually, north is like this. You know this symbol. The cross mean into the board, and south, if it is, if you want, then it will be like this: a dot and a circle. So our magnetic field, we don't know what the direction is. Okay, we really don't know. He's asking us to find the direction, the magnetic field. And we know something. It has to be, because we are talking about the Earth's magnetic field, right? Earth's magnetic field. Let's say we don't know what the direction is. He's saying this proton is experiencing a magnetic force upward direction. So the magnetic force is up. Velocity is east. So we know it has to be either north or south, right? Because magnetic force has to be perpendicular to velocity as well as the magnetic field. So now it's a reverse way of, we don't know what the magnetic field direction is, but we know it has to be perpendicular to the force. Force is upward. That means in a similar way, we have to say it must be perpendicular to both the force and the velocity. Magnetic field has to be perpendicular to both the force and the velocity. So it must be either north or south. How do I know? Let's say it is south. We don't know. It has to be either south or north. So let me say it is south and see if it gets the correct direction for the force. Right. So if I put it in the south, let me use the remote of my remote as the magnetic field. So it is pointing towards you, and the velocity is to the right or the east. So V cross B, I am getting it down. Am I getting the correct force? No, the force is actually up. So that means my magnetic field is wrong. It has to be other way. So I put it in the north. Then look at it. Velocity cross B, I'm getting the correct direction for the magnetic force. So the direction is north. What about the magnitude? Magnitude is simply the equation. That is easy. Right? There is no confusion there. Only the direction is a bit troublesome. But the magnitude, just the equation, you just substitute. Q is given, proton. Well, it is not given. It is probably in the formula sheet. Electrons charge and the proton's charge is 1.6 10 to the power minus 19. Well, this is a homework problem. And V is 1 10 to the power 5. And B is 55 microtesla. Multiply by sine theta. Theta is 90 because between north and east. So it's 90 degrees. Which is sine 90 is 1. Anyway, you take your calculator and solve it. You'll get certain answer. And that will be it. So I will not solve B and C. Please, I will leave it for you to do both B and C. Okay, let me go to the next slide. Now we start a new section. So in the previous section, section 3, we are looking at the magnetic force on a charged particle, a particle that is charged. Okay, so only when it moves, it will experience a magnetic force. Now here, again we are looking at a charged particle. We are continuing. Imagine we have a charge. Let me take a charged particle which is positive. So for easiness, we take positive, and it is moving in this plane. You mean the plane of this screen that you are looking at. Let's say at this moment it is moving up. It has a velocity up, and it is placed everywhere. Here we have a magnetic field shown with this green cross sign here. You know what it means? The magnetic field is into the board. Also, it is perpendicular to the velocity, right? So we have a magnetic field, a uniform magnetic field perpendicular to the velocity. The velocity is in this plane, and magnetic field is perpendicular to this screen. So the velocity of the charged particle is perpendicular to the magnetic field. Now let's see what happened. It will experience a force. By applying the right hand rule, the direction will be to the left. I can show you with my pencil here. Velocity is up. My pencil is the velocity, and the magnetic field is my remote. So it is like this. Now you bring your hand, V cross B. You must be curling your finger in the plane, in this vertical plane, and through the small angle. So you cannot go like this, you have to go like that. And the thumb is pointing to the left. So the direction of the force is correct. Okay. So this charged particle is having a velocity perpendicular to the magnetic field. It will experience a force to the left in the screen's plane. And what it will do, will it change the velocity? No. The force is perpendicular to the velocity. It will only change the direction. So it will experience a force this direction. So velocity now will be changed. Its direction will be changed. So it will be moving up while it is experiencing a force. So its velocity direction will change because of this magnetic force. Okay, the velocity magnitude will not change, only its direction will change. When it is there, again it will experience a magnetic force toward the center of a circle. So what will happen is it will just continue to move in a circular path. Okay, and wherever it is, suppose when it is here, you can look at it, and the force direction will be toward the center of the circle. So what happens to a charged particle when it moves in a magnetic field perpendicular to the magnetic field? It will start describing a circular path. This magnetic force causes a centripetal acceleration because there is a force to the center of the circle all the while, and will change its direction as it describes a circle. Now we can apply Newton's second law for this circular motion. So you can say force is equal to mass into centripetal acceleration. For the force, you will put this, because the magnetic force is Q VB sine theta. What happened to the sine theta? It is always perpendicular. V and B are perpendicular. Theta is equal to 90 degrees. Sine 90 is 1. So that's why it is not appearing. Equal to mass of the particle, centripetal acceleration. You learned this in your mechanics last semester. Centripetal acceleration is given by speed square divided by the radius of the circle it described. Now we cancel with a 1v on either side. Then you make the r as your subject. You get this. So the circle that it describes when a charged particle moving perpendicular to a magnetic field is given by this equation. And this equation also has a name, cyclotron equation, because it's cycle. It is going in a cycle, right? In a magnetic field, this charged particle is moving in a cycle. So there are certain experimental setup, which has a lot of practical application called the cyclotron. So this is called the cyclotron equation. So you can see this radius of the circle is proportional to mv. mv mean, we remember, is momentum. Mass into velocity is the momentum. So the r is proportional to the momentum of the particle and inversely proportional to the magnetic field and also the charge of the charged particle. So this is an important equation. It has many practical application in an experiment called the cyclotron. Right. So now also this comes in so many other application. Now let's see, what if the charged particle is having a velocity not perpendicular to the magnetic field, it also has a component parallel to the magnetic field, like here. So what we have here, along the x-axis, we have a magnetic field. And this charged particle is not moving, well, it has a velocity parallel to the magnetic field, also perpendicular to the magnetic field. Let's say in the y direction at this particular moment. So the velocity has component perpendicular to the magnetic field, also parallel to the magnetic field. So some direction. Magnetic field is in the x-axis, and the velocity has a component in the x-axis, also perpendicular to the x-axis. What happens now, because of the perpendicular component to the magnetic field, it will describe a circle. The parallel component will not be affected. The perpendicular component will change its direction because of the magnetic field, but the parallel component will not change because that component is in the same direction of the magnetic field. So due to the parallel component, it will not experience any force. So that parallel component will remain the same. So it has to move in the x direction. At the same time, it has to describe a circle because of the effects on the perpendicular component from the force. It has to describe a circle, and also it has to move in the same direction as the magnetic field. Both has to happen. What will be the result? It will go like this. It will describe a circle. At the same time, it will be moving in the direction of the magnetic field to end up making a spiral-like path. This spiral-like path is called helical helix or helical path. If the particle's velocity is not perpendicular to the field, the path followed the particle is a spiral. So we call that spiral path as helix. Okay, sometimes called the helical path. Yeah. Okay, so now let me summarize what we said. If a charged particle has a velocity perpendicular to the magnetic field, it will start describing a circle. But if it has a component also parallel to the magnetic field, then it has to do both. So in addition to the circle, it should also move along the magnetic field. So it will end up making a spiral or helical path. Now we can do this question. A charged particle enters a magnetic field of a mass spectrometer. So that's an experimental thing where you can use a mass spectrometer to determine what kind of charged particle we have. Okay, we send some charged particle. Suppose there are charged particle, you want to know what is it. We can use the mass spectrometer to determine that. So this question will tell you one such application. A charged particle, we don't know what it is. It enters a mass spectrometer with this speed, okay, very high speed, maybe from a nuclear reaction or something. It subsequently moves in a circular orbit with a radius of 16 centimeter in a uniform magnetic field of 0.35 Tesla, having a direction perpendicular to the particle's velocity. So as the particle enters this mass spectrometer, the mass spectrometer will apply a certain magnetic field perpendicular to the direction of this charged particle. Now you know what happened. We learned, right? It will start making a circular path. And they measure that circular path, the radius of that circular path, the R is this much. Now you immediately remember the cyclotron equation, which you can apply. The radius of the circular path must be momentum of the charged particle divided by QB. Now I can do some algebra here because the question is to find the mass to charge ratio of this charged particle. So I can move things, to either side of the equation. You get the mass to charge ratio to be equal to this. Radius of the circular path it is describing, magnetic field that is applied, and the speed of the particle. We know all of this. R we measure, B is what we apply, so we know what it is given to us. The speed is, it's coming out, somehow we measure the speed of the charged particle, so we know everything, it is given to us. Substitute, and you get this answer for the mass to charge ratio of this charged particle. Then you go to the table. We know from, experiments done before, if it is a hydrogen charged particle, okay, with maybe the electron is stripped, so hydrogen ion, a positive charged particle, its charge to mass to charge ratio is given in the table, 1.04. We are getting our charge to mass to charge ratio to be 3.13 in minus 8 when you do the experiment for this unknown charged particle. So it is not hydrogen. It is out. Do you see anything that is? Yes, this guy is the same as that guy. So we conclude it's a tritium ion. I don't know what exactly it is. It's hydrogen. They're all hydrogen. Hydrogen isotopes. So deuterium is a hydrogen with 2 protons. Yeah. Deuterium. No, that will be helium, right? How? What is the meaning of isotope? Isotope means chemistry.
Like the same, but it's different.
Yeah, suddenly I forgot what exactly an isotope. Right, hydrogen has, yeah, I know, 1 proton. Hydrogen means there must be 1 proton. But the mass is different. How? Hydrogen has no neutron, right? Deuterium has 1 proton and 1 neutron. So mass is double, okay? So, element is specified by the number of proton. If you have 2 proton, mean it is not hydrogen, it becomes helium. Anyway, so now I remember, right? Deuterium mean a hydrogen with a proton. Tritium mean a hydrogen with 2 proton. So the total mass becomes 3 times. Anyway, now you know it's a charged particle which is hydrogen, but an isotope with 2 protons with that. You can see the mass is tripling there. Yeah. Okay, so it's nice. So mass spectrometer is something that applies magnetic field to a charged particle, and looking at the radius, you can measure the, there's a way, the path will be shown, visualized, and then we can measure the radius and get the, determine what that ion is. Number 5, go to the next topic, which is what is the magnetic force on a current carrying wire? Magnetic force on a current carrying wire. What is current? Current means charges moving, right? So we already told you, we learned, if a charged particle is moving, it will experience a force. So wire means there are lots of these free electrons, those are charged particles, and not just one charged particles, a lot of them. So each electron, which are electron, going to experience a force if it is placed in a magnetic field, because these electrons are moving. So each of the electron will experience a force. That means the whole wire will start experience a force. So now we are jumping from single particle, charge particle, to the complete wire, which consists of lots of charge particle moving in the same direction, identical electrons. Okay, so the whole wire will experience a force. So we can do an experiment and see that. Okay, now here we have a wire, and this wire is placed in a magnetic field. So you know this shows the direction. So into the screen, and initially we have no current. Will there be force? No current means no force. There is no charge particle moving inside the wire, so there will be no force. Now we switch the circuit, send a current. You see the wire will be deflecting to the right, left, sorry, left. Okay, what does it mean? The electron that is moving inside will experience a force. So that means the whole wire, the entire thing will be experience a force. It says fixed at those 2 points. So it will be deflected to the left. How do I get the direction? Shall we get the direction by applying our right hand rule? So let's take just one electron inside. Electron is a negative charge, right? And it is having a current up mean electrons are moving down. You know the conventional direction of the current. Negative charge moves in a certain direction, current is in the opposite direction. So current is up mean, electrons are moving down, the velocity is down. And then we have a magnetic field which is into the board. Let me take my pencil as my velocity, so down, and my remote control as my magnetic field, which is into the board. Now you apply your right hand rule, start from the velocity. So I have to keep it like this, so I can curl it in this plane, the plane made by V and B. So my thumb is pointing to the right, but it's a negative charge. So the direction of the force is to the left. So we convinced, we verified, so that's correct, that's what happened. Now what if I switch the direction of the current? We'd expect the force to be to the right. Okay, so we don't have to go through that. So you see, when you do the experiment, that's what we get. Right, now good, very good. Can we get an equation for this current carrying wire? Yes. Without proving it, we can prove it from our previous equation, which is F is equal to QVB sine theta for a charge. But you can apply this and we can prove this. I don't want to bother you with all the details. I'll just give you the equation. The equation for the magnetic force on a current carrying wire is this. I is the current. L is the length of the wire, because if it's a long wire, the force will be greater. So it depends on the length of the wire as well. For the whole, what is the force on the whole wire? It depends on the length of the wire. B is the magnetic field. Theta is the angle between the current direction and the magnetic field. Okay. But instead of giving the direction to the current, we'll give the direction to the length of the wire. Okay. So it will be what direction the current is flowing through that length. Okay. So in other words, it is but we'll keep the I as a scalar. Okay. We will not make it a vector. We'll make the L to be the vector. Its direction is the current direct flow of the current through that length. Okay. So you can see that it is LB sine theta. You can make it into a vector product, L cross B, and the force will be F equal to I into L cross B. Now you know how to get the magnitude of L cross B. It will be LB sine theta. So that's it. Now this is the vector equation to get both the magnitude and the direction of the force on a current carrying wire. All right. So we got another equation. This is for current carrying wire, not for a single charge particle. I is the current. L is the length of the wire on which the force is acting. and it has a direction. If we treat it as a vector, it has the direction of the current through that piece of wire. B is the magnetic field. So now we can answer this question. A wire carries 22 amperes from west to east. So I will take the left side of me as west, right side of me as east. So the current is going in the direction of the current, or rather the L. Okay, the current is moving to the east. We have a current through the wire towards east. Assume the magnetic field of the earth at this location is horizontal and is directed from south to north. I'm going to, now this is the vertical, my screen imagines a vertical screen. Of course, for you it is vertical, but if you keep a piece of paper on the desk, it's horizontal. But anyway, here for me it is easy. So this is a vertical, and up will be this, not north, it is up, and down will be this. And can you tell me what is the direction of north? Into the board, right? Very good. So the direction of north will be into the board. So you can put it like that. Because if I draw like that, it is misleading, right? Because you cannot really do it. So I will say north is into the board and south is out of the board. So that is the symbol for out of the board. Now what? We have a question. And the magnetic field is given. It is into the board and north, and its value is this much. A, find the magnitude and direction of the magnetic force on a 36-meter length of a wire. Okay, you should immediately remember the equation. F is equal to I L cross B. So that means magnitude will be I L B sine theta. Just simply substitute. I is equal to 22. L is equal to 36 meters. B is equal to 0.5 10 to the power minus 4 Tesla. And theta is equal to north direction and east direction. L is east, right? The direction of the current flow. And B is north. East and north, what is the angle? 90. So sine 90. That's it. You substitute and get the answer. That shouldn't be difficult. You have the calculator, you substitute. What about the direction? Yeah. No. We are not getting the maximum value. We are applying to this particular question. What is angle? Angle is the theta is the angle between current direction and the magnetic field direction. Current direction is east, magnetic field direction is north. What is the angle between 90? It's not about getting the maximum value or anything. It is just finding out what theta is and substituting the value of theta into the equation. Okay, you are not asking about the maximum value or anything. It happens to be maximum value, and that is a different story. Yeah.
I get 0.039.
Yeah. Okay. I don't have the answer here, so I will skip that. Okay. Right. If you did it correct, it is correct. Okay. So I'm just telling you how to do it. And what about the direction? Right hand rule. Current direction is my pencil, and the magnetic field direction is my remote control. I am just holding it like that. Okay. Take your right hand up. Okay. So I will skip B and C. I want you to do at home, and it's not a homework, but better do it before you come to the class next time. Okay. So we did this. Okay, we are coming to a new section. Okay, this is very important section. It's getting a little bit complicated. I shouldn't say that. Right, now what happens now? We have a current carrying loop. Say it's a loop, right? It's a closed structure, so it's a loop. And we send a current through it. So, in the left-hand side, I have the pencil pointing like that. That means current is coming towards you. Here the current is going to the right. Here in the red sector, the current is going in. Okay, if I keep it like that. So there's a current that is flowing through this loop. So we have a current carrying loop. And suppose I place it in a magnetic field. Let's say there's a magnetic field horizontally to the right. What do you think will happen? It will spin. Yeah. Now we come to the electric motor. It will spin. Why? On this right hand side, the force will be up. On the left section, the force will be down. And on this one, when it is like that, it will be zero, but it will spin. Suppose it is kept, excuse me, come to the front and sit here, please. All the way here. So suppose it is fixed like this. On the right side, you can apply the right hand rule, and you will find your left side. Okay, this is the left side. The current is like that. You apply the right hand rule. L cross B is this, and there will be a force on this up, and the force on this will be down. Suppose it is hinged here. This will go like that. Now this is the situation when it is like that. And when it is like that, you will see there will be a force on this also. That force will be I, B. It will be pulling like that. So it doesn't matter. And this one will be pulling other direction. So only these two, there will be a torque, and it will be spinning like this. And when it is like this, the force will be 0. Why? So this is the direction of it will not be 0. Okay, the torque will be 0. I'll explain that. On this, the force will be up. On this, the force will be down. Is there any torque? No. Right? The torque will be 0. So we're going to get an equation without bothering you with the details. The torque acting on a current carrying loop, a loop like this, is given by this equation. Very nice equation. You don't worry how we get it. It can be shown easily, but it doesn't matter. You'll be given the formula in the formula sheet. All you need to know, if we have a current carrying loop, the torque acting on that loop is given by this equation. You know this symbol tau. We use the tau for something else, the time constant, right? And in torque also in semester 1 in mechanics. So this is also torque. It's a magnetic force acting on this current carrying loop. The torque is equal to B. That is a magnetic field where this is kept it, where we keeping this. And I is the current that is run through this coil. If there's no current, you cannot have any torque. Okay, it only for current carrying loop we will have a torque when kept it in a magnetic field B. A is the area of this current carrying loop. You understand? This is a rectangle, so you know how to get the area. Okay, right. And number of loops. Here we have only one loop, right? Sometimes we can have like this, coiled, and like that we can have several number of loops. So that is n. Theta is what? Theta is the angle between the perpendicular to the loop and the magnetic field direction. So suppose when it is something like that, the perpendicular loop will come like that, and this is the magnetic field, and this is the angle. The angle theta is the angle between perpendicular to the loop and the magnetic field direction. Okay, so we can see when theta is equal to 90, we have a maximum torque. When theta is equal to 0, that is like this, because the perpendicular is like that, magnetic field is also like that, in the same direction, theta equal to 0. Then the torque is equal to 0. We got one more equation now, right? We had a magnetic force for a single charge particle, then magnetic force for a current straight wire, a current carrying wire. Now it is torque, not just force, magnetic torque on a current carrying loop. We got this equation. Now we are going to do some more things on this equation. You saw that equation. Let me write that equation again. Torque is equal to what is it? B I A N sine theta. So that's what we had in the previous slide. And I'm going to collect these three terms and I'm going to call that as mu. This is entirely for the current carrying loop, independent of whether we keep it in a magnetic field or not. So for the current carrying loop, I can say there is an I for this. That's the current that is flowing through the loop. A for that. A is the area of the loop. And N for it, that means number of loops of that current carrying loop. So we are going to call this as the magnetic moment, and we give the symbol mu. So what is mu? That is a magnetic moment of this current carrying loop. It is equal to current through the loop multiplied by area of the loop multiplied by number of loops of that loop. And it has a symbol mu, the Greek letter mu. And we make it a vector. How do I make it a vector? Okay, I is a scalar, A is a scalar, N is a scalar. The scale, yeah, it is a scalar, but area, right? We can say that perpendicular to the area of this loop is the direction of the magnetic moment of the loop. But if I take this again, now you may ask, oh, perpendicular to this plane, okay? Is it up perpendicular or down perpendicular? Both are perpendicular. So two choices. If I say the direction of this loop is perpendicular to the plane of the loop, you are giving me a problem. But how do I choose? Which one choose? The upward perpendicular or the other side perpendicular? There is two directions. I have to get only one direction. The technique is you look at the flowing of the current and you curl your fingers in the direction of the flowing. Suppose here in our example, the current is flowing because this one is, anyway, let's say it is current is flowing like this, looking from above counterclockwise. If it is looking from above counterclockwise, so curl your fingers in the direction of the current. Suppose it is flowing like that, the thumb will show the direction, it's upward. So if it is flowing the other direction, clockwise, it will be down. So that's how we get rid of this ambiguity. So the magnetic moment has a value given by this expression IAN, and it is also a vector, and you know how to get the direction. It is perpendicular to the plane, but you have two choices. You get rid of the one choice by applying this right hand thing. Right, it's always perpendicular, but you should know how to get the right perpendicular direction. Now, this is mu, so I can write the magnitude of the torque as mu b sine theta. Now it gives us to make how torque itself is a vector, right? Torque is a vector. We have if it is in a two dimension, it can be counterclockwise direction, clockwise direction, which is again it give the counterclockwise direction. We can give a particular direction, right? So counterclockwise is not a direction. We do the same thing here. So we will say the torque vector is equal to the vector product of the magnetic moment multiplied by the magnetic field. So it correctly gives us the magnitude. Magnitude is mu b sine theta. So if we substitute mu is equal to NIA, we get the same exact equation for the magnitude. And when you write it as a vector equation, that will give us the direction of the torque as well. Now, it is mu vector product B. So with that, by applying the right hand rule, put your fingers along the magnetic moment and curl it towards the magnetic field, and then you will get the direction of the magnetic torque. So let's do this question. Example, we have a circular wire loop of radius 1 meter. So this is the picture A. We have a wire loop, okay, a current carrying wire loop. And the direction of the current, it is kept in a horizontal plane, and the direction of the current looking from above is counterclockwise, looking from above is counterclockwise. And there is a magnetic field in a certain direction. It makes an angle of, say, with the z-axis, z-axis is making an angle of 30 degrees. So this is given in the question. This radius of the circle is given in the question, 1 meter, and the magnetic field strength is given in the question, 0.5 Tesla, and the direction is also given. It's making a 30 degrees with the z-axis. And the current in the loop, I, is also given. Question A, find the magnetic moment of the loop and the magnitude of the torque at this instant. Right. So magnetic moment is mu, and you should remember, even if you don't remember, it is in the formula sheet. It is simply equal to number of loops of the current loop, I, the current through the loop, A is the area of the loop. Substitute. N is equal to, is N given? How many loops do we have? It says a wire, one circular loop, okay? So that N is equal, A mean 1, right? Otherwise they will say there is a wire loop having 100 turns. So 100 is the N, but here it is not so. It's saying a circular wire loop. That means N is equal to 1. I is the current through the loop, is 2 amperes. What about the area? Area is, how do you know the area? What is the area of a circle? Area, this is a circle. There is no length for pi r square. This is something you have to remember. Area of a circle, this is a circle. So the plane of this wire loop is a circle. So you should know how to get the area of the circle. Area of a circle is pi r squared. So r is 1 meter. So you substitute 1. So you get the mu. You get certain value. Done, but we are not done. We have to now find the magnitude of the torque. Now tell me, mu is a vector, right? Mu is a vector. We got the magnitude. What about the direction of mu? It must be perpendicular to the loop area. So it either has to be positive z or negative z. Both are perpendicular to the area. It says it is positive z. How do you know it is positive z? How do you get the area? Can you tell me? No, direction of the area. How do you get the direction of the area? Yeah, area value is pi r square, not r square, pi r square. How do you get the direction of the area? Yeah, say this is the loop. The current is flowing like this, looking from above. So curl your finger, it is pointing up. So positive z direction is the direction of the magnetic moment. Direction of the magnetic moment, okay, I keep saying area. The direction of the magnetic moment will be, you curl your fingers, right hand fingers in the direction of the current and look at the thumb. Thumb is pointing up. So the magnetic moment direction is in the positive z-axis. The next question is the torque. Torque is equal to mu b sine theta, the magnitude. So mu is equal to whatever value you found from previously, b is equal to 0.5. The angle between b and mu is 30 degrees. So sine 30. Okay, so you just substitute and get the value of the torque. But I can ask you another question. What is the direction of the torque? It comes from the mu cross B. As a vector equation, I can write the torque is equal to mu cross B. So you point your fingers in the direction of mu and see whether you can curl it towards the B. So this is mu, let's say my pencil is mu, and my remote control is the B. So mu cross B will be into the board.